Graduate Society. Because
It's part of the Engineers Australia. Ask some students some questions, get more student involvement.
haven't approached me. So I'm in chemical and we have something called SMOOS, Monash University Chemical Engineers Society.
Yeah.
And they take a survey from the students about how the classes are going after 3 weeks.
I think that's what's happening today and for me, yeah.
Oh, for you, right. For me, it's on Thursday.
Oh, is it?
Yeah.
Thanks.
That's fine.
Sorry?
Are you Eric? Or?
No, Sean.
Sean, okay. This is not Henge 4700?
Yes, it is.
Oh, cool. Sorry, I was just, did you see the email from the department about the survey at the start of the class? Or?
Yes.
We were just discussing.
Oh, are you here to do the survey?
Yeah,
okay,
great. I'm Connor. How are
Nice
you?
to meet you. Yeah, good.
That's good. It only takes about 5 to 10 minutes. So
Oh, cool.
it's just, the only thing I would ask is if you could step out the room while we're doing it, if that's okay.
Oh, yeah, sure.
Not yet, that's fine. Wait till there's more people.
Do you need slides?
I've already got it. It's only one slide, so.
Oh, but you're plugging in?
Yeah, if that's okay.
Yeah, cool.
Thanks so much. Sorry to be a hassle. It won't take
No,
long
it's
at all.
fine. It looks like no one's here yet anyway,
Yeah.
so...
I thought that might be the case so far, so.
And are you using this?
No.
Okay. Well, feel free to... Sweet, so you just come get me when you're done?
You can just be around now?
Yeah, I'll just hang out outside.
Yeah, sure. Cool. Thanks so much.
You don't need me to announce anything or anything?
I'll do it, yeah. G'day guys, just a really quick one. So I'm from the Department of Mechanical Aerospace Engineering, like you guys are obviously. We're just running a really quick survey in week 4, so as well as the set use where you get to add your feedback for the next people that run the unit. We're also getting you guys to provide feedback in week 4 so we can improve the unit while you do it and make sure the lecturer's doing a great job, where they can improve, what they're doing really well. So if you could log on to that link, the actual survey takes about 3 minutes. More detail you can go on to that up. And just fill it out really quickly. All the survey responses are completely anonymised, so none of the actual feedback will be related to at all. It just goes through a bit of a report, which we give to Sean, and then he can sort of take on that feedback and report back to you guys if there's anything he wants to say, anything like that. So if you just log on, like I said, it'll take like 4 minutes. Then we're really cool. Thanks. live stream. Cool. Thanks heaps, guys.
Everyone's sorted. Hopefully that was entertaining. I have no idea what just happened, but we didn't get very much notice about it. All right, everyone can hear me? So last week you all, for everyone that was here, you had a really nice lecture from Uli Steinzeifer, so I hope everyone enjoyed that. A lot of the information that he gave you will be really useful for your projects, and also if you're interested in ever developing a medical device later on in life, I really highly recommend you keep those slides. They're incredibly useful. I know I have a copy as well. So today we're going to be talking about cardiovascular sensing, which is going to link back to the work that we covered in week 2, which was about the theory of sensing, an introduction to sensing principles. So this is going to be more of an application-driven lecture. We're going to talk about some examples of sensors that are used in a medical space, in this case a cardiovascular sort of space. We'll talk about some sensors and also some devices that use those sensors as well. So what we'll learn about today is sensors for cardiovascular applications and cardiovascular devices and the sensors that are using them. Imaging is not covered today. That'll come later with Steve, not necessarily for cardiovascular, but in general. And I should make a disclaimer that this lecture really only scratches the surface of sensing in medical applications, and definitely only scratches the surface of cardiovascular sensing. There is a lot more out there to be discovered. And if you're interested in some of that, I've put up some post-reading for you, link on the Moodle. Go to Implantable Sensors for Heart Failure. It's in Circulation, which is a really good journal. So there's something interesting there for those that are a little bit more interested in this work. So if we look at different sensors for cardiovascular applications, there's a lot of things that we need to sense to really diagnose what's going on with the patient and monitor them. So there's some examples of some sensors and what they're essentially used for up on the screen. You know, we have heart rate, that's a pretty obvious one, but what we can get out of that is mean heart rate, looking at nocturnal heart rates as well, what's happening to your heart rate, variations throughout the day. Also the variability of that heart rate, and we'll talk about the clinical significance of that a little bit later. Accelerometers are a really commonly used thing for cardiovascular applications, particularly looking at physical activity. Impedance, we'll talk about a little bit about what impedance is and how it's used a little bit later, but for fluid status, particularly anything to do with movement of fluids or volumes of fluid. Then we've also got hemodynamic, in this case pressure, so looking at mean pressures within the system, change of pressures with time, so dP dt, and also looking at real-time pressures. We'll go through pressures a fair bit later. Doppler is something that can be used, so it's sound essentially, looking at cardiac output or blood flow. Cardiac output equals blood flow. We'll talk about that later as well. We can also look at heart sounds. Again, this is a pretty basic one, but you can look at that for peak endocardial acceleration, movement of the heart. And then, of course, chemicals. There's a lot of sensors looking at pH, electrolytes, glucose, things like this, and biomarkers looking at inflammatory responses and so on. Now, as I said before, this lecture does only scratch the surface of cardiovascular sensing, so we can't get through all of those today. These are the main ones that we're going to focus on for today's lecture. So they'll be looking at heart rate through electrical sensors, and then we'll touch on the other ones for various sensing technologies. So the actual sensors that we will talk about include electrical sensors, in this case just for ECG as an example. We'll also look at some flow rate sensors, particularly useful for cardiovascular, because your cardiovascular system pumps blood, so the flow that comes out of that pump is particularly important. And within that, we'll look at Swan-Ganz catheters, which are basically a catheter they put in your artery. The USCOM device, which is ultrasonic cardiac output monitoring device. And then we'll also look at impedance cardiography, which is another fairly non-invasive way of measuring cardiac output. And then we'll talk about a couple of different pressure sensors that are available for cardiovascular applications. And then we'll talk about the devices that can use some of these sensors, and also looking at smart devices. Now, there will be a couple of activities throughout the lecture today. Hopefully we'll get time to complete them and get through all of the content. So just kind of pay attention a little bit as you go so you can contribute to the activities, and if I ask you questions, you might be able to answer them. So, okay, let's start on the electrical sensors. So we're just going to go through how ECG works and its applications. I mean, everyone here knows about an ECG, right? I don't know if you do any experiments on that, if you do any biomedical instrumentation where you make your own ECG. Some people are nodding their heads. So you've done that in a unit already? You made your own ECG at Monash? Oh, great. Okay, yeah. So I did my undergraduate biomedical engineering degree at QUT, and they have a unit biomedical instrumentation that everyone has to make an ECG. It's the easiest thing you can get them to do in those units. So, I mean, it's pretty simple. Basically, it measures the electrical activity or depolarization. So that's basically what the cells do. So the depolarization, it's essentially the cells shift in electric charge distribution. So it's measured in millivolts, so it's a fairly small thing to pick up. So the sensors obviously have to have quite a decent gain to convert that to anything. And The old ECGs, at least the ones, you still see some of these in medical clinics today. They print out onto a piece of paper. A lot of the newer ones, they'll just be on a monitor, of course, but as an example of how you can use gain of a sensor, which we spoke about in week 2, the standard paper deflection, 1 millivolt equals 10 millimeters deflection on the paper. So you can measure how many millivolts you're actually recording by looking at the deflection on the paper. And the standard paper moves at 25 millimeters per second, so that's how the doctors can look at the depolarization versus time. It's usually measured with surface sensors, so you can see them up here. This is an example of the 6 that are placed on the chest. It conventionally uses between 10 and 12 electrodes. Only actually needs 10, but it's typically called 12-lead ECG as well. And by the way, ECG also means EKG. They're exactly the same thing. But related to these sensors, so you have to place them along the chest. So you have 6 overlying the heart, and then you have 4 from the limbs. So you have 1 on each hand and 1 on each leg as well. The incorrect positioning of these sensors can obviously significantly change the result that you're going to get. So how the electrical conductivity of the heart essentially works, and then how it's sensed by these electrodes, is you start basically, I should probably briefly explain cardiac anatomy first for anyone that's not aware of it. This is a very poorly drawn cross-section of the heart. I didn't draw it, I just got it off Google. But if you start at the top here, you have the atria, which are chambers that receive the blood from the body and then pump them into your ventricles. So you have your right ventricle here and your left ventricle here. Your ventricles then contract and pump the blood around the body to the lungs and to the body. In between your ventricles, you have your interventricular septum here. And then at the top of that, you have your atrioventricular or AV node. Okay? So the wave of electrical depolarization spreads from the atria down the interventricular septum to the ventricles, and it usually is read a little bit more to the left due to the heart's position to the left, and also the fact that the left ventricle contracts a lot harder. Okay, so the direction of that travel is known as the electrical axis, and it's measured by those recording leads. If you just had 2 of them, you could still detect an ECG, but you wouldn't get the direction as well. When the wave travels toward a recording lead, it results in a positive upward deflection on the trace, and I'll show you some example traces later. And away from the lead is obviously negative or downwards. So here's a really nice picture that I found, which sort of describes what an ECG looks like and what happens at each of those points. So to start with, we have a P wave here. So basically what we have is the P wave. This is the small positive inflection before the large peak. The large peak is called the QRS complex, and then you have the T wave afterwards. So this P wave here is a very small depolarization from the ventricles. So you'll see that basically it's an electrical, from the atria. It's a small electrical impulse that travels from the sinoatrial node up here to the walls of the atria, causing them to contract. Now, a lot of people think that the only thing that contracts in the heart is the ventricles, the 2 big chambers that are down the bottom, but it's not true. So what actually happens is the atria contract first and push some blood into the ventricles to fill them a little bit before they contract. It can contribute up to about 30% of the filling of the ventricle, and if your atria stop working, which can be called atrial fibrillation, you get a lot less blood pumped around the body because your ventricles don't fill quite as well. So this initial step is quite important for filling the ventricles and for pumping out enough blood. And then what happens is you get a little bit of a delay here. So this impulse that has travelled from the sinoatrial node down to the atrioventricular node is actually held up by about 0.1 seconds. And this, basically what this is for is to allow the contraction of the atrium to push fluid into the ventricles and allow those ventricles to fill before they contract. So I guess kind of accounts for some fluid momentum. Whoever designed this was quite clever, obviously evolution. Then what we see is the bundle branch, it's carried, the electrical signal is carried down, the bundle branch is to the right and to the left. And then basically we see contraction here, which is this large QRS complex as it spreads through the ventricle walls, and then we see that contraction. Now, the final pulse here, this is actually just from the ventricles relaxing. That's when they start to fill up with blood. And that happens passively as the valves open. So there's a recognised normal range for these ECG intervals, and this helps clinicians sort of identify when there's a problem, when they can pick this up. So of course these values change quite a lot patient to patient. You might see that these are actually these values are in milliseconds, not a percentage of the cardiac cycle. So for instance, if a patient's heart rate increases, you would obviously expect those ranges to decrease quite a lot, okay? So for instance, these are usually measured between different points on the waves, and these are the very common intervals that are used to diagnose different problems. So we have the PR interval. You can probably guess this is from the point of the P wave to the point on the R wave. QRS is just the QRS complex, so that's this entire section here. And then we've got QT, so we start at Q and then we go to the end of T, and that's the normal ranges for that. So we can then use this ECG, as I've sort of explained, to diagnose a lot of issues. Even geometrical changes to the heart can result in changes to your ECG, quite significantly actually. If you look at this case, this is a fairly normal heart geometry, a little bit more accurate than that sketch that was on the previous slides. And then if you have some abnormalities, in this case, this is an abnormal tricuspid valve that you can see here compared to here, and then you also have a very enlarged heart here as well. You could detect that using an ECG and a lot of other problems such as electrolyte imbalances, if the patient is having or about to have a heart attack. Ischemia essentially means a loss of blood supply, and which results in scar tissue to an area in the heart, so it's a little bit of the heart tissue that dies. Abnormalities in the heart rate, that's obviously very common, heart rhythm abnormalities, and also a lot of other medical side effects. And I've put a couple of examples of what you might be able to detect using an ECG. These are just two very simple cases. The first is sinus node disease. So a lot of the times when you're a little bit older, you start to have problems with the sinus or the atrioventricular node. And it has trouble transmitting those pulses. So often in older patients who have lost the ability to spontaneously depolarize, when I say spontaneously depolarize, basically that means they've lost the ability for their heart to beat sometimes. And you can see that's happened here. So we get a very normal looking ECG here. We still get all of these waves. And then all of a sudden we miss one. So we've essentially skipped a beat there. It's not that uncommon. Has anyone in this room ever felt their heart skip a beat? I would be surprised if everyone doesn't put up their hand if I asked you to, because it's actually a very, very common thing. No, you haven't? No? It's very, very common to happen at least sometimes. Sorry? No. Well, no, it starts again itself. If you have to bang it to start again, there's obviously a bigger problem here. It's quite common just for the heart to just occasionally, maybe once every few months, you just sort of, for those of you who haven't felt it, you can have a slight, you just sort of feel it get a little bit bigger and then it just contracts again the next beat. It just misses a beat. There's a few surprise faces around. It is quite common. So that's something that can be quite common. Of course, in patients where it happens a lot more often, then it's a problem. If it only happens occasionally, it's not really a problem a lot of the time. So particularly this can cause slower heart rates, pauses, which are not such a problem, but ceasing altogether, that's when it definitely becomes a problem, because obviously then you don't live. Then another case is down the bottom here. So this is what's called an atrioventricular block. So this is again often in older patients, particularly with a damaged atrioventricular node, and it can lead to a delay or failure in conduction of the ventricles. For example, if we look at the P wave here, it's quite close to the QRS complex. And then if we look at the next cardiac cycle, the P wave is a little bit further away from the QRS complex. And then again with this one, again it's a little bit further away to the stage where you actually miss out on a beat, a heartbeat here. And in this case, you can see that, well, sorry, in the top case, you can see that you just completely miss the heartbeat. Your atria don't fill the ventricles, you just have absolutely nothing. In the bottom case here, you can see that the P wave has still happened. So in this case, the atria have still contracted, they've still pushed some blood into your ventricles, but your ventricles haven't contracted then. So what you might see on the next heartbeat is, again, your body will push more blood into the ventricles, they'll get a little bit bigger and they'll contract a bit harder. Okay, so the next heartbeat will just be a little bit more forceful to push that fluid out, and hopefully it's not a problem if it doesn't continue and continue. So it's not just about looking at the ECG when we're measuring heart rate or using an ECG. It's not just about looking at that trace. It's also about looking at your heart rate and the variability of your heart rate. For instance, short-term heart rate variability is actually used to predict sudden cardiac death. For instance, this is so we can even stratify the risk of these patients according to their heart rate variability. So for instance, if we record heart rate variability in some patients, we can class them as low risk, medium risk and high risk. And you can see the low risk patients have a survival probability of 96% after 1 year, so quite high. Whereas then the medium risk and the high risk, we can see much higher mortality or death rates, just based solely on looking at your heart rate variability. It can also predict the requirement for hospitalisation 3 months before it's required, which is quite impressive actually. These patients can actually know that they'll need to go to hospital, and they can actually plan for these things. They can go in and see their cardiologist a lot earlier if they know something's going wrong. So device-derived heart rate variation in combination with physical activity data can be used to risk stratify patients with heart failure, which is what we see on the right there. So that's kind of what I wanted to talk about on the ECG side. We'll now go through quite a bit of detail on cardiac output sensors. Now, cardiac output just means flow. So it's the output of your heart. Your heart outputs a flow rate of blood. So that's essentially what we're looking at. We're looking at the flow rate of blood coming out of the heart. Okay? So it can be used to determine patient state, essentially, how healthy or unhealthy you are. A few things that you can use for that mean cardiac output. You can look at the pulsatility as well, using cardiac output. So this is an example of a cardiac output trace. I'll use this one actually. Everyone knows that you have 4 heart valves. We saw them on one of the previous slides. Basically, your aortic valve is the big one that pumps the blood around the body. What we see here is when the heart contracts, the flow rate out of the aortic valve increases very, very, very quickly. Goes up to quite a high value. This is in milliliters per second, and then comes back down again when the heart's finished contracting. You can also see we often get a little negative part here. That's because as the heart valve closes, a lot of the time you get just a small amount of blood travelling back through that heart valve. This is in a patient with a healthy heart valve. If someone had a failing heart valve, you would see that negative period actually come down along here like that. And then what we see after the heart has finished contracting, the mitral valve then opens, so the heart then starts to expand, which means the flow rate through the mitral valve increases, and then it drops down a little bit. And remember how before I said in the P wave, you get that atrial contraction, which contributes to your filling? That's what this second mitral valve spike is here. So that's what happens in the P wave. So we can measure the pulsatility of this cardiac output. Obviously, high pulsatility is good. It means that your heart's contracting quite well. If it's not very pulsatile, then that means your heart could be starting to fail, or that you're just resting. We can also look at valvular regurgitation. As I mentioned before, if we see the flow rate coming down negative here, then obviously we have some valvular regurgitation. The problem with valvular regurgitation is it essentially just means less forward flow. If you're pumping 5 litres a minute forward and then your valve is letting a litre or two go backwards, then you're only pumping 3 or 4 litres a minute. So to get your flow rate up to 5, your body then has to start pumping 7 or 8 litres a minute, which requires a lot more work by your heart. It can eventually lead to heart failure. So we can also look at septal defects. Does anyone know what a septal defect is in the heart? Exactly. So it's a hole between the heart chambers. It can be the ventricles or it can be the atria. So the atria at the top or the ventricles at the bottom, you can have a hole between them. Apparently about 25% of you will have an atrial septal defect, which is a small hole in the upper chambers of the heart. Some of these are clinically significant, most of them are not. A little bit of sharing of blood between the two sides of the heart is generally not too much of a problem, but a larger hole is. And if it's in the ventricles, then it's a much bigger problem because the pressure difference between the ventricles is quite high. And if you have a hole there, then it's going to push a lot of blood from the left to the right ventricles.
Could you pick that up by checking the SpO2?
Sorry?
Could you pick that up by checking the SpO2? Would you then have less oxygen?
Potentially. There could be other reasons for that, though. I mean, the way I think you'd pick it up is just an echocardiogram, an ultrasound of your heart. But yeah, I mean, you would see decreased oxygenation, so it could be one of the reasons why you would see that. Yeah. And you can also detect a lot of other problems in the heart just using cardiac output as well, because as I said, the heart's a pump. We detect problems with the pump by looking at the flow rate out of that pump. So we have a few ways of detecting cardiac output. None of these are perfect. You can't just cut a person open and then let them pump their blood into a bucket and measure the volume change, because that wouldn't work so well for them. So we have to look at other alternative techniques that can be used for this application. So we're going to talk about 3 different techniques today on that. The first one is the pulmonary artery catheter. Second one is the ultrasonic cardiac output monitoring device. And the third one is impedance cardiography. You can also use imaging modalities. Some of you might have heard of 4D MRI, which is essentially an MRI scan where they can actually look at the flow rate out of your heart. But that's quite complicated, and as I said, we're not doing any imaging in today's lecture. So, first of all, looking at the Swan-Ganz catheter, it has several different names. You can call it a Swan-Ganz catheter, a pulmonary artery catheter, or a thermodilution catheter. So this is used to measure cardiac output in patients. It's quite invasive. It has to be placed inside the pulmonary artery of the patient, which is not an overly easy task. And it's completed during a lot of cardiothoracic operations. You can also use it as a pressure sensor. It does have pressure sensors on it. And these are actually used to guide the sensor into place, but then can also be used for diagnosis of the patient afterwards as well. So, did that go too far? No. So the way it works, as I said, it's usually inserted into the pulmonary artery. In this case, it's via a vein in the neck. So this yellow part here is the pulmonary artery catheter, the Swan-Ganz catheter, inserted into the neck, into a vein where it goes down through what's called the inferior vena cava, this blue vein here. It then goes through the right atrium, and then through the right ventricle, and then bends around into the pulmonary artery. Now you can imagine something like this is quite challenging to navigate. How do you actually do that in a patient without opening them up? And it's quite neat actually. It uses fluid momentum to essentially carry itself through. So when it's inserted, a balloon is expanded, and then because the blood flows around this way anyway, the balloon is kind of carried around that way into the pulmonary artery. So it's a fairly nifty way to get your sensor into position. And then once you do get it into position, the balloon can then be deflated. And the way you detect if it's in position is, as I mentioned, it has a pressure sensor on it, on the tip of the catheter. So as it comes through, first of all, we know what right atrial pressure typically looks like. It's a very small oscillation in pressure, so we know we're in the right atrium. We then go through the right ventricle, and typically right ventricular pressure goes between about 2 millimeters of mercury and 25 millimeters of mercury in a regular peak and trough. Then, when we see it go through the pulmonary artery, it goes between about 25 and 10 to 15. So we see a change in pressure as it's going through. We know exactly where it is. So it's a very neat device. This is essentially the way it works. So once it's in the pulmonary artery, the clinician injects a bolus, or essentially a volume of fluid, cold saline in this case, into the catheter. So it has a hole that goes all the way through it that can carry that fluid. So the clinician from outside the body injects the cold saline through that port. That cold saline comes out in the right atrium, in here, and then it travels through into up here, into where we have a temperature sensor on it, and then we can use the time essentially that it takes for the cold to come through here and be measured as a way to calculate cardiac output. And if it just changes, here we go. So the way we do that is using the equation on the top here. So we include the volume of the injectate, the temperature of the blood, which we can usually assume is a certain temperature. This might be an assumption. In cases where it might be a little bit different, the clinician can also put that in. We have to put in the temperature of the injectate, and this is usually controlled before they put it in, so we know what that is. The specific gravity of the injectate, that's usually that's something that is set. We know what that is. And same thing with the specific heat, because we know what the fluid is. The specific gravity of blood and the specific heat of blood are also known constants. So essentially we only have to put in a few parameters, and then it uses the area under the curve to essentially calculate what the cardiac output is. Now, the area under the curve, of course, if you put a cold fluid into a system, into a loop, because you have to remember your blood circulation is a loop, eventually that cold fluid is going to make its way back up, and then you're going to see that small change again. In reality, you don't really see that kind of change because your body has auto-regulation of your temperature, so you don't really see that continuation of cold fluid. So we just kind of assume that the temperature drops kind of like this line, and then that's how we calculate it. So that's how and I say estimate cardiac output here. It's a measurement, and it's the gold standard for measurement of cardiac output in patients, but it's still an estimation. We don't know exactly what the flow rate is coming out of the heart. Based on this, there are several assumptions to this. So some of these assumptions include the physiological conditions have to remain constant. So this is the patient has to be still, the patient's heart rate can't be changing, the heart contractility can't be changing. There's a lot of things that can potentially change, and we're assuming that they don't. We're also assuming that all the heat exchange occurs between the indicator and blood without surrounding tissue heat loss, which is another incorrect assumption, but can be potentially negligible. We're assuming that the mixing of the blood and the injectate is completed upstream of where that temperature is measured. Again, there's some error in that. We're also assuming that the sensor is sufficiently sensitive, accurate, and responsive enough to detect those temperature changes. We learnt about all of those things in week 2. So we would have to then, of course, characterize the sensitivity, accuracy, and responsiveness of this sensor. And we're also assuming a consistent injection by the user, because obviously if you're injecting this fluid quite quickly compared to someone that injects it quite slowly, you're going to see a very different curve. You're going to see the blood mixing quite differently as well. So this was something in my previous laboratory in Brisbane. I had a laboratory inside a cardiac hospital, and the cardiologist didn't actually believe the results coming out of these things, and so they wanted us to test them and see how accurate they were. So that's what we did. We evaluated the intra-operator variability on cardiac output measurement using the thermodilution method in vitro. So, as I said before, there's no perfect way to measure the cardiac output in a patient. You cannot cut open their aorta and see how much blood is pumping out. It's just not possible. So the way we decided to do this was using an in vitro system called a mock circulation loop. Which is a mechanical representation of your heart and circulatory system that beats just like your normal heart. It carries fluid around with the same specific heat and so on as blood, same temperature as blood. And we use that with calibrated flow sensors that we could calibrate to 99% accuracy, about these were, to compare the pulmonary artery catheter. So this is a schematic diagram of what our mock circulation loop looked like. It doesn't probably make a huge amount of sense, but trust me, that equals that. Essentially what we have here is the left side of the heart, the atrium, a heart valve, the left ventricle, and a heart valve. This is essentially the body. And then we have the right side of the heart, same thing, couple of heart valves, atrium and ventricle. And then we have the lungs here. And then we simulate the same blood volumes and everything as well. So this system that I actually built in my garage at home is shown on the screen there. Now you can see it just looks like a whole bunch of pipes that were built at Bunnings, and it's pretty much what it was. Most of this is bought at Bunnings or places similar, but the data acquisition systems that we use to run this are worth about $100,000 and underneath the bench, away from the fluids because they damage it. So basically what we have in here is systemic and pulmonary circulations. We have pulsatile flow. We have what's called the Frank-Starling response, which means that as your heart gets bigger, it contracts harder. So the mock loop has automatic feedback responses that are the same as what your body does. It has variable healthy and pathological conditions, so we can simulate pretty much any patient you can imagine. We spoke about holes in the heart, we can simulate that in there. We spoke about heart valve disease, we can simulate that in there. We can make the ventricles contract harder or softer. We can change the resistance to blood flow, how stiff your arteries are. We can change the fluid volumes, and we can use it for evaluation of devices like this. So, again, it might look like it was built in Bunnings, but it's actually the most advanced system in the world for this kind of technology. And the reason I can say that is because I built the second and third most advanced systems in the world in Germany and Malaysia. So, it's pretty cool. And this is the kind of output that we get from this system. So you might remember in, I think it was the second week of this unit, I spoke about sensors can also be used for the evaluation of devices. This is one example where we use sensors for the evaluation of devices. We have a lot of pressure sensors on here, we have flow sensors on here, we have volume sensors on here as well. So that way then we can look at exactly what our patient, in this case our mechanical patient, is doing. This is what the pressures look like in most of you right now. So this big jump here is the left ventricle pressure. This dotted line up here is your aortic pressure. If anyone's been to the doctor and had their blood pressure measured, got a value of about 120 on 80, that's 120 on 80. So that's kind of what you're looking like at the moment. This is the pressures in the right side of the heart. This is the flow rate coming through the heart or the cardiac output. And this is the left ventricular volume versus pressure. You don't have to worry too much about that. So what we did is we modified this mock circulation loop to look at this pulmonary artery catheter. We put in a heat exchanger to heat the whole system up to 37 degrees. We plugged in a pulmonary artery catheter into our mechanical patient. And then we randomly adjusted the flow rate through the circuit simulating different patients between 3 and 8 litres per minute. So that's a pretty standard cardiac output range. We're not exercising, we're just sort of hanging out and not doing much, or maybe we're standing up and sitting down, things like that. And then we blinded several experienced physicians, so these are very experienced doctors that are used to using the pulmonary artery catheter, and we asked them to determine 4 different cardiac output settings. So they would inject the fluid in there and they would do it 3 times, at least 3 times, to make sure that their values were within 10% of each other, and they would tell me what the value is. It was really good for me to see how bad experienced doctors are at doing these sort of things and how much I can't trust them. So then we used statistical models to compare our results. This is basically what we observed. So we had 15 participants, 10 male, 5 female. Specialists were in consultant cardiology, intensive care, and cardiology advanced trainees. Average age is about 40. We also looked at BMI and grip strength, because your grip strength reflects on how forcefully you inject the fluid through the circuit, which we thought would be the primary correlation between grip strength and accuracy. We were certain that's what our results were going to say. And for fun, we also looked at right heart experience, so how many these people had done, so whether they'd done this in 10 to 25 patients, 25 to 100, or greater than 100, how experienced the people were. This is basically what we found. This is our measured cardiac output versus actual cardiac output. What we noted was participants tended to overestimate cardiac output with a mean difference of 3/4 of a litre per minute. So if you were to do this clinically, if you were to say that a patient is pumping 4 litres a minute, you might think that that's totally fine, but in reality they might only be pumping 3.25 or 3. And in this case, the patient could actually be quite sick. So it's very important to know the error of your sensor in this case. But also we saw an R-squared value of 0.85, which for an engineer sounds terrible. For a clinician, that's actually really quite good. So that they were quite impressed with what they'd done. And then if we divide this data by the experience of the clinicians, what we found was that the operator experience was actually the only variable predictive of cardiac output measurement accuracy, with a pretty good p-value. So basically, the more you do it, the better you are. Ended up being the conclusion of this study, which was a slight letdown, but the fact that grip strength wasn't related to it, we thought was quite interesting. So that was the only thing that really correlated: grip strength, age, gender, BMI. None of that was predictive of the accuracy. Our study did demonstrate the need for adequate training. Basically, we showed that the more you use it, the better you get. So the more training you can do is obviously a good thing, and that our mock circulation loop could actually be an ideal training tool for clinicians to use for this kind of thing. So we're going to quickly cover the USCOM device as well before we have a break. So this is quite a nifty device that was actually invented in Australia and is used all around the world to measure cardiac output, particularly in patients that need very quick diagnosis of what their cardiac output is. So it uses a Doppler ultrasound probe, you can see it here, that's applied suprasternally, so it's just kind of on the chest, just above the sternum here, and it's facing towards the arteries here. So you get pretty close with this probe. And it estimates the aortic or pulmonary valve cross-sectional area, and then it uses Doppler to measure the velocity. And if we know the velocity in the area, we can calculate the cardiac output, obviously. You can also input the valve diameter if you don't think it's doing a very good job of estimating this. So the way it essentially works is it sends ultrasonic pulses by the transducer. What happens is stationary particles will always send back the same signal. So it has some software filtering that basically just filters stationary things out, whereas moving particles send back different signals. Now, interestingly, here you can see in basically how it calculates the velocity of the blood. I mean, it's going to have some Doppler things there. It's going to need to know the speed of sound in the tissue. But we've also got the angle of incidence between the ultrasound beam and the direction of flow. And that's something that's important to take away from this message, is that if you're using ultrasound to determine what your cardiac output is, then you need to have this, it needs to be aligned with the flow, or it needs to be it needs to have some kind of correction algorithm for misalignment. So basically this is what the USCOM device looks like. It uses that theory. It's based on algorithms from babies that are 23 weeks old up to 86-year-old adults. So it's got its mathematical equations are built in, but then it's also being tested in a wide range of patients to sort of correlate it and validate it a lot better than just having those equations alone. And it's validated in the range of 0.12 to 18.7 litres per minute against the current gold standard, which is the Swan-Ganz catheter. But as we saw earlier, this technique is fairly prone to error, so might not be the best validation that you can use in the world. Well, it still probably is the best validation you can use in the world because there's not many other options. It does require alignment. So as I said before, it's placed suprasternally. It has to be facing towards the vessel, so you have to align it very carefully with that vessel. Remember, the angle of that alignment does affect the readings, which can be challenging to use in patients that are moving around. And considering this device is predominantly used in emergency situations, sometimes you're going to have patients that are in a lot of pain and moving around, which can be a little bit of a problem. So again, we decided to evaluate how good it was using our mock loop. Now, I don't need to describe this again to you. You've already seen what it is. I'm sure you understand it just as well as I do by now. But basically what we did is we put the USCOM device on our mock loop. We got some experienced clinicians to put it on and try and measure the cardiac output from our loop. Again, very similar to the last study. If this changes... Okay, so again, we randomly adjust the cardiac output, in this case between 2 and 10 litres per minute, because we know this sensor is meant to have quite a large range. I said before about 0.1 to almost 20 litres a minute. We blinded the physicians again. We asked them to determine, in this case, 9 different cardiac output settings that we randomly changed. We were changing things like heart rate and blood flow as well. This is particularly useful because the USCOM can be used to measure heart rate as well. Basically, if we look at, you can see the pulses going through there. If you know that the time that it takes for these pulses to happen, of course you can work out heart rate very easy. So that was another thing. We just wanted to test the heart rate monitor for it as well. The physicians had to perform a minimum of 3 measurements to ensure they were within 10% of the result again, and we used some statistical methods to correlate this. So in this case, these are the results that we got out of our mock loop. So we could see the cardiac output varying as the heart pulsed. And then these were the results that we got out of the USCOM monitor, which I don't know if you remember looking at that picture of the USCOM monitor before, but they're actually surprisingly similar to what you see in patients. So this kind of shows us that the flow rate coming out of our system is actually quite similar to what patients have, which is a good thing. And then if we look at the measured heart rate, and we know what heart rate is in our system because we control it. We use solenoid valves to control our heart rate. We get it. We know exactly what it is. If we compare our heart rate, our known heart rate, against what the users estimated, this is for 3 different users. You can see user 1 got pretty spot on. There's a couple that are off. User 2, I think, realised that we were varying it in 5 beats per minute increments and got it absolutely perfect every time, so they kind of outsmarted our testing. And user 3 was also pretty close. And then if we look at the cardiac output, in this case 1, 2 and 3, we can see that all 3 users got quite close to what the measured value was. Which we thought was quite interesting. We were expecting dramatically bigger changes than that. And so we really did notice a very strong correlation with the estimated and measured cardiac output using the USCOM across the full range that we tested. It was interesting though, users did tend to slightly overestimate the cardiac output, and that was particularly at the higher flow rates. And they did report difficulty measuring the cardiac output at low flow rates. It took them several attempts to get those 3 successful that I spoke about before. So there's just a couple of potential limitations with this device. Overestimation at high flow rates and difficulty in using them at low flow rates. So before we go into this, we might just have a quick 5-minute break. If everyone could come back at about 3 o'clock, we'll continue. We do have a little bit to get through today just because we missed what happened with the questions earlier. All right. Thanks, everyone. We'll get started again now. I just wanted to address two common questions about the stage 1 project that you're submitting. First of all, there's been a question about the similarity scores with Turnitin and if your references will affect that. That's a very good question. I can't remember the people that brought it up, but very clever. They won't be. We've turned that off. So there's been a few people that have already submitted them, and it's not picking up the references as similarities. So that should be fine. And also the other thing is that the groups need to be finalised by Thursday this week. If you don't have a group, or if you have any problems with your group, whether it's someone has nominated himself into your group where you didn't know them or something like that, just send us, myself and Steve, an email, and then we can sort that out for you. So we need to have the groups sorted by Thursday, and we also need to know the clinical problem by Thursday as well. Because that's going to help us break you all up by demonstrator. So if you haven't emailed me your clinical problem by Thursday, then I might just end up assigning it to you. So make sure you do that by Thursday at the latest, please. Okay, so are there any questions on that, by the way? No? Everything's fine? Okay, great. So moving on with the lecture. So we're going to talk briefly about impedance cardiography, which is another way of measuring cardiac output. So for those of you who aren't aware, impedance is essentially the effective resistance of an electric circuit to an alternating current. So it's not just resistance, you also have reactance, which gives you a bit of it gives you phase and magnitude. So impedance, and if you want to learn more about that, then there's plenty of things to look at. Guys, you just need to be quiet. So it essentially uses the changes in transthoracic impedance during cardiac ejection to calculate the volume of blood pumped out each beat, which is the stroke volume. If you know the stroke volume and you know the heart rate, then you can calculate the cardiac output because you just multiply the two. It requires 6 electrodes in 3 pairs. So one pair is for the ECG, or in this case EKG, it's exactly the same thing, and then 2 to detect changes in impedance. And then what we see is high frequency, low magnitude current produces a baseline impedance. So you get a baseline impedance across the electrodes, and then you will get a changing impedance which then correlates to the stroke volume of blood coming out of the heart. So it uses the impedance waveform, so that it uses the ECG, it uses the impedance waveform and also the first derivative of that waveform to calculate cardiac output. Now we don't need to go into the very specific workings of the device because it's extremely complicated and I don't even know what they are, to be honest, all of the calculations that are done behind the scenes. But it's just important to understand the basic theory of how that works. And the fact that it can be used to measure cardiac output. It can also be used to measure the resistance in your body to blood flow. So this is called your systemic or your pulmonary vascular resistance, and that resistance is related to if the patient has hyper or hypotension, high blood pressures and things like this. So again, we did a study of this in our lab. We didn't correlate it with our mock circulation loop this time because if you put a bunch of electrodes on the mock circulation loop, you won't actually see anything. So in this case, we used some humans. So we took measured data, which was the cardiac output, heart rate, stroke volume and resistance, to 50 healthy humans doing exercise on a stationary bike. And on the next slide, I'll show you what happens when you go from lying down to standing up and back to lying down again as well. They were the 2 activities we looked at. And you can see the results on the right there. So there's some pretty interesting observations. First of all, we get very little noise with heart rate. It's pretty decent there. As you would expect, it's using an ECG, so you should be able to detect heart rate pretty well. But when we start looking at stroke volume, there's a substantial amount of noise in this case. You know, the error obviously in this signal due to noise is quite significant, but we can still use that as an estimation of what the stroke volume is of the heart. Stroke volume is the amount of volume that comes out with one heartbeat. If we multiply the stroke volume by the heart rate, we get the cardiac output. You can see in this case the noise level is about in between the two, as you would expect. And what we see that is another interesting observation, although this is a little bit expected, is that when you go from resting, which your body pumps out about 5 litres a minute, which you can see happening right there, to exercise, in this case 60 watts of exercise on a stationary bike, you can see a very rapid increase in the flow rate to about 8 litres a minute. And this is what you would expect, this is what your body does. You jump on an exercise bike and you do a little bit of exercise, the flow rate goes up pretty quick. However, if you keep doing that for a couple of minutes, what can happen is you get maybe a little bit tired, and then if you're asked to do a lot more exercise, in this case doubling the exercise capacity on the bike, moving up to 120 watts, it takes your heart a little bit longer to ramp up in this case, which we thought was a fairly interesting observation. So that was just an example trace as well. That wasn't a mean trace of 50 people. That was just one example trace that was quite normal, and as is this. So this is a postural change. So as I said before, you're going from lying down, standing upright. So lying down here first, and then standing upright, and then you settle, your heart rate settles, and then going back to lying down again, and then everything settles. And what is interesting here is that we don't see as much noise in the transducers, which is potentially because of the fact that the patient isn't moving around. If you're exercising, even if it's a stationary bike, you're going to be moving around a lot, which is going to, as you're shifting around and you're measuring impedance across 2 points, it's going to vary a little bit, so you're going to get a little bit of noise. Yes? So it essentially, if you think about measuring the resistance in an electrical circuit, it's kind of like that. And the resistance essentially, it has resistance plus reactance, which has a phase as well. But if we just sort of really simplify it, we're talking about measuring the resistance to the circuit between 2 points. Now, as your blood flows, that resistance will change. Okay? And so you can actually pick that up on the waveforms. And so we can look at the waveform and then also the first derivative of that waveform to essentially make an estimation of what the cardiac output is. Again, it's not a perfect way, and in fact it's actually quite inaccurate, but it's a very non-invasive way of measuring cardiac output. So what we see here again is quite low noise in this case for stroke volume, and if we multiply that by your heart rate, again you're getting your cardiac output. What is interesting here is that the response when we're measuring cardiac output is actually very similar to exercise. It's just like a very short period of exercise, and when you think about it, that's kind of what laying down to standing up is doing. We were expecting much different, very different results to this, because typically what happens is when you go from lying down to standing up is a lot of the blood volume pools down in your legs and changes your cardiac output a lot. But we didn't see that. So basically the result of this was that in this particular case, what the patient is doing produces a lot less noise. So in some applications, your sensor might work quite well, like in this case, because it's obviously very prone to changes in the patient's state, to moving around and things like that. So that's just something to think about when you're designing your sensor, basically everything that your patient will be doing when you want to measure anything. So we also used that impedance cardiography results, this is just an interesting little study that we did, to validate our mock circulation loop. So we basically took the measured data, the mean data from all 50 patients. We then replicated the heart rate, resistance, cardiac output and stroke volume changes that we saw in those patients, the mean values, into our mock circulation loop, just to make it closely represent humans even more. So that way then all of the pressures and flow rate changes that we see in our mechanical person, they're quite realistic. It's just an interesting little study that we did. So now we're going to have a little discussion where you're going to choose a sensor for different applications. So I'm going to There's some, now I should note that all of these values are actually made up because I didn't have time to look up the real values other than this, which I happened to stumble across. So don't take these as real values for these sensors. But these are just as a guide. If you were given all of these values for each sensor, so the sensitivity, the range, the response time, the error at 5 litres a minute and the resolution, for the 3 sensors up above, which sensor would you choose for various clinical applications? So for anyone that doesn't have these slides, maybe take a quick photo of this now. And then, because on the next slide, I'm going to show you some clinical situations, and then you're going to discuss which sensor you would use. All right, everyone's got that? So these are the cases that we have. So we have 3 different patients, and you're going to tell me which sensor we should use. So case 1, Kathy is a 65-year-old with no prior cardiac conditions. She's still relatively active and wants to get an approximate idea of how much her cardiac output changes when she lightly jogs on a treadmill for 20 minutes in the morning. Case 2, George is a 45-year-old patient who has had 2 previous heart attacks. He's undergoing invasive surgery to correct his aortic valve, and his surgeons need to very accurately monitor his cardiac output. And case 3, Frank is a 52-year-old who has come to the emergency room complaining of chest pains, fatigue and trouble breathing. The emergency medicine doctor needs to quickly and accurately assess his cardiac output to identify the problem. So for the next 5 minutes or so, speak with the people next to you, and we'll have a discussion about which case would use which sensor and why that is. And just so you know, it's not necessarily one sensor for one patient. You could use the same sensor for all 3 if you think that's the best option. So have a chat for 5 minutes, and then I'll walk around with the microphone and we can discuss. All right. So most people seem to have decided which ones they would use. Just in saving time, let's just do a show of hands rather than too big of a discussion. So case 1, who would go for the USCOM device? No one? What about the Swan-Ganz? No one? And impedance cardiography? Some people don't want to measure the cardiac output at all, that's fine. Correct. So obviously impedance cardiography here is a much better sensor to use, particularly for its invasiveness. So we don't want to be putting in catheters in healthy people. Really, we don't want to expose them to those sort of complications. Case 2, who would use impedance cardiography? No one? Okay. Who would use Swan-Ganz? A few. And who would use USCOM? A few. Okay, that's an interesting one. So this one, he already, in this case, George already is undergoing open heart surgery, essentially. So putting in a pulmonary artery catheter is probably a better idea. USCOM is not going to do much in his case. In case 3, who would use impedance cardiography? USCOM? Almost everyone. And Swan-Ganz? No one. Again, correct. So the majority wins here again. This is an emergency room, so we're looking at how quickly we can measure this. If you're putting in a Swan-Ganz, it's obviously quite invasive. Impedance cardiography takes a while to set up, and it's not that accurate anyway. USCOM is a good option in the emergency medicine room. So in case you didn't realise, all of this was for nothing, and that's why I didn't actually bother getting correct values in there. The lesson from this is more, it's about the application and the safety of the patient sometimes, not just about the gains and sensitivities and response times of the sensor. Okay, so a clinician will always keep the patient safety first. Of course, when you're designing your sensor, you want them to be as accurate as possible, but you need to think about the application and if the clinician would put it in the patient. Because if the clinician's not going to put it in the patient, your sales are not going to be very good. So, very sorry for tricking you. I think most people saw right through it anyway. So now we'll move on to pressure, and we will probably cover this fairly quickly because we still have a little bit to get through. So, pressure sensors, I think we're just going to quickly cover 3 different pressure sensors. So first of all, just looking at a basic pressure cuff, I think I should have a prize for anyone that can actually pronounce what it's technically called. I'm not going to try. But basically it's an acoustic sensor. How it works, if you've been to the doctor, if you've had one of these tests, is they put a cuff around your arm, they inflate the cuff to a very high pressure where the artery closes, and then the old style ones use a stethoscope to actually hear the heart sounds themselves. The new ones do it automatically. But basically you can't really hear anything at that point. You can't hear any blood going through there because it's closed. The pressure is then released slowly until you get to this aortic pressure here, the maximum pressure. And at this point, the artery starts to open. It starts to force its way open, and you can hear that. You can actually hear the artery opening and closing. And then you continue to release that pressure until the artery is completely open, and in that case, you can no longer hear anything. The maximum value there and the minimum value are your systolic and diastolic aortic pressures respectively, or the maximum and minimum pressures in the vessel. So it's a pretty easy way to do it. The next one that we look at is, this is very commonly used in the hospital. If any of you have been in an intensive care unit, you might have seen these sort of pressure sensors. We use a lot of these in our lab, actually. They're reasonably accurate. They're typical clinical transducers that use a strain gauge. So it consists of a flexible membrane which sits in here. That basically blood comes in, I can see it a bit easier here, blood comes in through here. This is connected to a blood line inside the patient that's invasively inserted through a needle or a tube sort of thing. And then this tap is opened, and then there's a flexible membrane in there with blood on one side and atmospheric pressure on the other side. As the blood pressure changes, the membrane in that sensor deforms. Okay, so you have a deformable component here, a mechanical component, and that causes strain of what we're going to look at on the next slide. And strain, essentially, the deformation of that flexible membrane can then be measured electrically using a Wheatstone bridge. So for the electrical engineers in the room, you can probably explain this much better than I can, but for everyone else, it's a fairly simple circuit. If you have an inlet voltage or a voltage coming in here, basically, and you're measuring the voltage between B and D, if all of these resistances are the same, then there's not going to be any voltage difference between these 2 points. Okay? If one of them changes, then in this case R4, then there will be a voltage change between those 2 points, and you can calculate it using this. So in this case, you could make basically a resistor on your deformable membrane that as the resistance changes, your voltage across B and D changes as well. So you can use multiple arms of this as well, depending on the application, but for simplicity's sake, we're only going to talk about changing R4 or RG. And we're not even going to talk about that much. So the output voltage is expressed in millivolts, output per volt input, and that's converted using a gain and offset to pressure. But it's these blood pressure gauges, these ones, are actually very, very prone to offset error. When you plug them in one time, the very next day you can plug them in and they will be recording something completely different. So can anyone sort of give us an idea of how we might be able to overcome that consistent offset problem? So basically the answer is recalibration, regular recalibration. And we have to do that quite often. So if we go back to look at this sensor again, the advantage of these sensors is this three-way tap here. So as I said, the blood comes in here through there onto the membrane. Basically, whatever way this arrow is pointing is off. So what you can do is flick this arrow around to here, expose the pressure sensor to atmospheric pressure. You can re-zero the sensor because we zero to atmosphere. Then flick the tap back around to this way, and then we're measuring pressure again. Okay, so it's a very simple calibration step, just calibrating against atmosphere. Obviously, if this was an implantable component, something sitting inside the patient, there's no way you could do that. Okay, so that's where it's just important to calibrate your sensors often. Going ahead to the next sensor, because we do need to get through these a little bit quickly, is the CardioMEMS pressure sensor. These are actually starting to get implanted in quite a few patients around the world. They're quite neat, actually. They essentially have no power source on them at all. They can stay inside for quite a long time. They're miniaturized wireless pressure monitoring sensors, so there's no wire that comes out of you, and they can be fed into various vessels, particularly the pulmonary artery, which goes to the lungs, is a common place to put them in. And they're implanted via the leg, so they basically go in the leg and they get fed up to the pulmonary artery, kind of similar to how the Swan-Ganz gets inserted, but through the leg rather than the neck. They have these two loops on them, which serve as anchors to keep them in place. And they're used as a guide for heart failure progression and proactive management to reduce hospitalisation. So if the clinician knows exactly what kind of pressure you've got in the pulmonary artery, they can then assess you sort of week by week or whatever. So you do require some anticoagulation with these sensors. Having anything inside the bloodstream, you're going to require a little bit of anticoagulation so it doesn't build up a lot of clots on it. But it has resulted in a 37% reduction in heart failure-related hospitalizations, so it's quite useful. The way it works, it uses microelectromechanical systems, or MEMS. It has a coil and a capacitor on this on a tiny little electric circuit in it, and this sort of resonates or vibrates essentially at a specific frequency, right? When there's pressure applied to a membrane in there, or a pressure sensitive surface, it changes the frequency that coil and capacitor vibrate at. Now, what makes them vibrate is an electromagnetic coupling via an external antenna, which powers the device via RF, radio frequency, and continuously measures the resonant frequency. So basically, it has no power at all in it, sits inside the artery there. You put a transmitter on the outside of your chest, which applies a RF signal there, which makes it oscillate, and the frequency of that oscillation changes depending on the pressure inside the vessel. And then you can also wirelessly then detect, it wirelessly then transmits back to that same thing that sends the RF signal out to tell you what the pressure is. People can do this at home. That's the really big advantage of this. It's not just an in-hospital device. Patients can do it at home, and then the blood pressure is uploaded to a secure website, and then the clinician can keep track of you, which is very, very neat. The same company also released what's called the EndoSure. I'm not sure if it's still clinically available. I haven't seen them recently, but it's used to measure the pressure in an abdominal aortic aneurysm, which, to briefly explain, your aorta is the large vessel that carries blood from your heart to the rest of your body. It sort of curves around to the left and a little bit back in your body, and then it goes kind of straight down before it splits for the legs. It's basically a tube that goes from the top to the bottom, and it's quite straight. Some patients have a thin-walled section that kind of overly relaxes and balloons out. So it'll go down straight, and then it'll balloon out, and then continue straight. That's called an abdominal aortic aneurysm. The problem with these is that if they expand out too much, they can burst. And this is the highest pressure blood vessel that you have, and if it bursts, you can bleed out in a matter of minutes or even seconds. So what this thing does is it's implanted in there to keep track of the pressure in that vessel. It's deployed in the aneurysm sac, and it's kept in place by these little loops that are around it, or the basket. It has plates that have a variable separation based on blood pressure. So as the blood pressure changes, the plates sort of come in or out. Okay? And then essentially, again, you apply resonant frequency to these plates, which vibrate at a certain rate, and the rate that they vibrate will change the pressure that's measured. But again, I'm not too sure if they're still used. So quickly, we'll go through another choose your sensor case. So we might just have a couple of minutes for this. So these are the same patients. So Kathy is now 68 years old. She's still relatively active and gets regular checkups at her GP. She's never had any cardiac events before, but was feeling faint during a morning exercise recently and wants to know why. Case 2, George is now a class 2 heart failure patient of 4, there's 4 classes of heart failure, and is currently taking regular medication to maintain his cardiac function. His doctor wants to regularly monitor his condition to keep on top of his medication before his condition progresses too far. And then Frank has been admitted to the intensive care unit after his cardiac event and is being closely monitored. His doctors want to closely monitor his blood pressures while he's there to predict upcoming cardiac events. So a couple of minutes, and then we'll do another little survey to see what everyone thought is the correct answer. All right, that's probably enough time for that, so we'll skip through this pretty quickly. So, case 1, who thought cardiomems? Okay, who thought strain gauge? So an invasive one. And who thought a blood pressure cuff? Yep, agreed. So obviously something that's not invasive doesn't really need to be in this case. Case 2, who thought blood pressure cuff? Who thought strain gauge? And who thought cardiomems? So yes, I agree in this case. This is a patient that's going home, and so it's important to keep on top of it. We could also use, they do have take-home blood pressure cuffs as well, which a lot of patients use also. But in this case, it's much harder for the doctor to regularly monitor that because he's not going to be getting that data all the time. Case 3, who thought strain gauge? Yeah, who thought cardiomems? And no one thought blood pressure cuff, right? Excellent. Again, correct. We can move on from there. So now we're going to quickly go through some cardiovascular devices that use sensors. Some of the examples that I'm going to be talking about are intra-aortic balloon pumps, extracorporeal membrane oxygenation, ventricular assist devices, and also some smart devices that use sensors to actually control them. Now, some of you will already be aware of ECMO and VADs from the projects, if you've read the PDFs on them. I'm not going to give anything away that's going to help with those projects, so don't get too excited to the people who've chosen projects 1 and 2. I'll try not to anyway. So first of all, devices that use sensors. So if you're a heart failure patient and you're kind of at the end of the road, the pharmaceutical therapy is not really working anymore, you come into hospital and sometimes one of the first devices that some centers use is an intra-aortic balloon pump. It's a balloon essentially that's inserted through your leg into your femoral artery and then fed up into your descending aorta. You can see it right here. It's a giant balloon that sits in your aorta. It runs on helium. The reason it uses helium is if it ever does split, helium can get absorbed, whereas just regular air will just cause massive coagulation, embolus, and then you'll die pretty quickly, usually. So it's inserted in the femoral artery, driven to the descending aorta. And interestingly, it's triggered using blood pressure or ECG. So these are things that we spoke about before. In this case, it would use a strain gauge measurement for blood pressure, or it would use the ECG signal on it as well. So it's pretty cool that it's actually a very early device that uses sensor-based control as feedback to control a device. There's a lot of talk these days about personalising devices and getting them to respond to the patient, to kind of be one with the patient. But there's some problems with getting approval for that. But in reality, the intra-aortic balloon pump has been doing that for years. It responds to the patient, it speeds up, it slows down depending on what the patient is doing. So it already has kind of a control system built into it. This is kind of how it works. So when your heart is filling, that's called diastole, so it's not contracting at the moment. So there's no blood coming through the aortic valve, so that's when the balloon expands. That pushes some blood up to your aortic arch, which feeds blood into your coronary arteries, which feeds the muscle of the heart, and also the branch vessels on your aorta, which go to the head, neck, and arms as well. So it increases the perfusion of the blood flow to your heart and also to your brain, which is a useful thing, and then it pushes the rest downwards, so it increases the cardiac output a little bit to the rest of your body. And then when your heart is about to contract, it deflates, it actively deflates. When I say actively deflates, it actually applies a vacuum pressure to deflate. It doesn't rely on the blood pressure around it to squeeze it closed. It actually sucks all of the air out of that. And what that does is it creates a reduced pressure in your aorta, which means your heart doesn't have to pump as hard when it's pumping the blood out. So it kind of draws some of the blood out. So it's kind of a neat device for that. The advantages are it's less invasive than the rest of the devices that we're going to talk about, and it can be used for temporary support. The disadvantages are that you can have balloon failure, you can get infection from them. You can get something that's called an embolic shower, which is basically where you get tiny little blood clots all over the balloon, and then when it inflates at some point, it just releases all of those blood clots, and they go to the brain and various other parts of your body, which is not very nice. The other disadvantage is it doesn't do a whole lot. It only increases the cardiac output a little bit. So for patients in really severe heart failure, it's not going to keep them alive, really. So that's where the patient might then need to progress to ECMO, which is extracorporeal membrane oxygenation. It has an external pump and oxygenator, which are attached to the patient via tubes called cannulas. It can be used for fairly rapid cardiac or so heart or lung support, or both. And it's still less invasive than what we're going to talk about soon, which is ventricular assist devices, because it's essentially tubes stuck in your legs. You're not cracking open the whole chest. So it can be used for infants and adults and relies on pressure, flow, oxygen, CO2 monitoring, among others. In this case, it doesn't have an automatic feedback system, kind of like an intra-aortic balloon does, but the clinician will act as that feedback system. They will get all of the data, they will find out what's happening to your blood, they will find out what's happening to the flow of oxygen through there and the flow of blood around, and then they will change the settings. Yes?
Is there a reason why there isn't an electronic feedback system?
Hasn't been done yet. Yeah. So some people have done a little bit of research on feedback systems for these devices. ECMO, not a whole lot. There's a little bit out there that people have done, but generally speaking, not a lot. In VADs, there's been a little bit more that we'll talk about soon, but there should be. And so our group, Andrew is up the back as well, looking at doing that.
Is there much motivation for that? Or?
Yes. Yeah. So if we can develop feedback systems for devices like this, one, it takes the clinician partly out of the equation. They don't need to monitor them. ECMO, you have to have one-to-one monitoring. A clinician, a doctor or an ICU, doctor or a nurse has to be there with you at all times. You can imagine how much that costs. The daily cost is something like $3,500 to have a patient on ECMO in the intensive care unit. So if we can take some of that out of the equation, then obviously we're saving money, we're saving resources, and we're also taking away clinical mistakes. But there's also problems with having automatic control systems as well. For instance, let's say the sensor gain that we spoke about in week 2, say there's an error in it, a gradual error, and it keeps moving like this, or an offset error that keeps moving like this. What you're recording isn't the real value, so the control system's not going to get where you need to be. It might say your pressure in your heart might be, say, 10 millimeters of mercury. It might be reading 70, so it's trying to speed up and pump blood around the body at 100 litres per minute. There can be problems with it. Like any kind of man-machine interface, there's going to be problems. If you've seen Terminator, you'll understand a lot of problems that can be associated with these things. So back to ECMO. You can use ECMO for veno-venous support, which is essentially support of the lungs. This is often via the right femoral vein, goes through a pump and an oxygenator, and then often the blood comes back into what's called your right internal jugular vein through your neck. So basically it takes blood out and puts blood back into pretty much the same spot. The problem with that is when it puts blood back in, some of the blood that it's put back in just circulates straight back out again, so you get some recirculation in the circuit. But it's a good alternative to positive pressure ventilation, which can damage the lungs and keeps patients alive that have respiratory failure. Then you also have veno-arterial ECMO. I don't think I actually changed the picture there, sorry. So this is respiratory plus cardiac support. So in this case, rather than coming back in through the neck, this is the wrong picture here, it would come out through the femoral vein and go back in through the femoral artery, which is a different location. And in this case, it would provide heart and lung support. And it allows for respiratory and cardiac recovery, or it gives you a bridge to transplant or to a more permanent option. And it's a little bit lower cost than a VAD, which we're going to cover now. So ventricular assist devices, as many of you are aware, this is a pump that really takes over the pumping function of the heart. It's not a pacemaker. A lot of people ask me, when I describe VADs, they say, is that a pacemaker? No. A pacemaker is used to control the rate of the heart. A VAD takes over pumping blood around. Okay? So you leave the heart in place and you support it in parallel. So it's attached to your left ventricle, it then pumps blood around to your aorta. So your left ventricle usually pumps blood to your aorta. The VAD does exactly the same thing, just via a different line. So it assists it, it helps it, pumps blood around the body, keeps you alive. It can be used as a bridge to decision. This is where if the patient comes in a very bad way, there's some VADs that can be implanted quite quickly to get you through until they can make a proper clinical decision, until they can get all of the data from the patient that they need. Then it can be used also for a bridge to transplant. This is for patients on the transplant waiting list but can't get one. A lot of the time that can last for a couple of years. So you need a way of keeping blood flowing around your body until you get that, so they implant this as one of the options. It can also be used as a bridge to recovery, which is where you implant the device, your heart gets better, you take the device out and you don't need a transplant. And then probably actually the most common application at the moment around the world is for destination therapy. This is for patients that are not eligible for transplant and they just in a pretty dire situation, they're going to die without it, so they get this device for as long as they will live with it. Luckily, some patients who aren't eligible for transplant get the device, they recover a little bit, and then they can actually go on the transplant waiting list again, so then they can change their clinical indication, and then they can be moved over to a bridge to transplant. But the survival rates with VADs is actually quite good, so destination therapy isn't that bad. The current generation does last for greater than 10 years in some patients. There's a few patients that have lasted longer than that. And again, you have regular pressure, flow, blood monitoring by the clinicians. The clinician is your feedback loop and what changes the device operating conditions. But we want to move away from that. So, we're sort of running out of time. The VADs have 3 different generations. The first generation, I think I showed you in our first lecture, it's a very large pulsatile device. Second generation is a continuous flow axial or centrifugal pump that has some kind of mechanical contact. And third generation is a zero contact rotary blood pump, some kind of axial or centrifugal device that has magnetic levitation and control systems in there, so there's no mechanical wear. This is the 1-year survival with the first generation devices. Medical therapy, so just keeping the patient on pharmaceuticals after 1 year, only 25% of patients were alive. So 3/4 of the patients were dead without these VADs. So it's a pretty terrible outcome. That's how bad these patients were. Putting in this device kept survival up to 52%. More than double the survival just with medical management. So a really wonderful thing. But then as we develop the devices further, we're now seeing 1-year survival is 86% with these devices. And these are the sickest of the sick patients. These are in ICU. They're a lot of the time have some other kind of organ failure. They are in really bad strife. And for 86% of them to be surviving after 1 year is amazing, particularly when you think that 1-year survival with heart transplant is 85%. So we've actually met or exceeded the survival of heart transplant with a ventricular assist device. It's just as good as a heart transplant as far as survival goes. You have a lot of complications with these things still, and that's something that we need to work on and improve. The patients are staying alive. The problem is, if we look at a heart transplant survival curve, they're getting up to 18 years. VADs just aren't up to that stage yet. They haven't even been around clinically long enough to try them for 18 years. So we aren't at this stage yet. We probably can't even make a survival curve for 10 to 12 years because we have so few patients being supported for that long, but we will get there eventually. So that's the role of people who work on these devices that are improving them to get our survival curves out this far and hopefully up this high. But then we want to make these devices smart. I said that the clinicians are the control systems for them, but they shouldn't be. So there is a growing trend towards making these more patient-specific devices, whether that's geometry or actually making them smart. So geometry is, of course, making devices fit to certain patients. You know, taking patient scans, designing the device to actually fit in, whether it's a skull implant or an artificial heart or anything like that. But the performance is the one that we're really focused on, and sensors can be used to make sure the device actually responds to that patient and not just any arbitrary value that a clinician has picked. So that's the question that I guess we were just talking about before: what happens if it all goes wrong? There is always a possibility that the sensor will fail, and if the control system doesn't recognize that, it will respond to that failed signal and produce some kind of response that is very undesirable and could kill the patient. And in this case, we have to think about, at the moment, if the device is implanted into a patient and the clinician sets the speed too high and the patient dies because of that, who gets sued? It's probably going to be the clinician for negligence, or it's just going to be ignored. They're going to say it was just normal. If the pump goes in with a control system and the control system is what fails, then who gets sued? That's the company. So would the company want to implement a control system? If they know if something goes wrong that they get sued for it, it's the same thing with driverless cars. If we have driverless cars and everyone starts crashing, whoever makes the driverless cars are going to get sued. So it's something that we kind of need to overcome before we really look at control systems. But there are some control systems available in medical devices. Pacemakers use control systems to control the rate. We also see the artificial pancreas, which injects insulin, measures your glucose, and then uses a control system to inject it. So they do exist, and they do exist, or they are under development with ventricular assist devices. For instance, active control is something that we're working on in our laboratory, and Andrew Stevens, one of the demonstrators, has done his PhD in this area. He's very good at it. Basically, we use pressure inside the heart to control the speed of the pump. So if the pressure goes up, we increase the speed, reduces the pressure down, and so on. But we're also developing passive control systems. It doesn't necessarily need even a sensor for this. If we can have some kind of mechanical component that changes its shape or changes its performance based on the pressures or the flows in the circulation, we can actually get rid of the need for a sensor, and then we don't need to worry about those sensor problems. Then just briefly, the FDA actually had a public workshop on the physiological closed-loop control of medical devices back in 2015. So they do want to see this happen. They do want to see devices become